For those of you who have not heard about Fidelity, we're a multinational company providing financial products and services which strengthen the financial well-being of our customers. We like to think of ourselves as a technology firm that provides financial services. We're part of the event streaming platform at Fidelity, and we provide streaming capabilities enterprise-wide for a wide range of applications with varying criticalities, latency requirements, and just diverging needs overall. Today, we'll talk about how we enable these different applications to share data between each other.
So before we begin, let's talk a bit about the de facto problem of size and complexity that large organizations face. For organizations with hundreds of applications, thousands of topics, streaming millions of events every second, what should their Kafka cluster topology actually look like? We have a lot of options, but let's go ahead and start with the simplest approach first. Let's have a single organization-wide Kafka cluster that all teams across the organization can onboard to. Administratively, this appears to be quite nice. In this example, A and B here represent two different applications with their own unique sets of topics for their individual data streaming needs. Now, with just these two applications in the picture, we don't really seem to have too many problems with this. But what happens as more and more applications onboard to the cluster? Well, the picture should start to say it all. The cluster is becoming cluttered, and we risk noisy neighbors impacting other users sharing the same infrastructure. Let's take an example of this. Let's say, in this case, application D here is not business critical. It suddenly starts to take a lot of incoming traffic, more than is usual. This could impact the system-wide resources of the cluster and impact other users sharing the same infrastructure. Now, you can account for this by appropriately setting producer and consumer quotas, but that's not the only issue that can impact other users. Let's say client connections to these topics in app D fluctuate rapidly. At worst, consumer group rebalancing could recur. And again, this is another scenario that would impact all of the system-level resources of the cluster. And the blast radius for this could be too large to contain. So let's go with a different approach now. Let's say instead of a single organization-wide Kafka cluster that all teams share, let's break it out. Every application is put on their own dedicated Kafka cluster. This does reduce the issue of noisy neighbors that we just introduced, but it comes with its own set of problems. Administratively, this can be a nightmare to handle. Think about the process with all of these clusters to perform broker upgrades, rehydrations, rolling out new features, making config updates to like Kafka settings. All of these routine tasks that you may have to perform regularly with this scope of clusters can be just a massive burden for administrators. That's also not even getting into the conversation of over-provisioning, especially if we need to have identically configured twin clusters stood up in alternate regions to allow teams to fail over to. So we've introduced two extremes. On the one hand, a single large cluster may be great on a good day, but it can just be a massive outage waiting to happen. On the other hand, individual clusters do provide the isolation that we're looking for, but operationally and financially, they can be a massive burden. So what can we do about this? Is there some way that we can get the best of both worlds? Is it possible to create medium-sized clusters? And if so, how should we do it? Can we group by use case? We'll move on to talk about Fidelity's approach to these questions.
Thanks, Michael. So in this presentation, we'll go over how Fidelity handles cluster topologies and how we isolate individual use cases while allowing them to still share data across clusters and across use cases. When we took this on, we had a question about our presentation, and we said, how do we present something that's both very advanced and also bring value to everyone, regardless of where they are in this Kafka journey? We're about 8 years in on this platform, and so overall, we have a lot of experience here, and that may not translate well to somebody a little bit earlier on in the presentation. So one thing we're going to do is provide a 7-part strategy here on our data sharing model within Kafka. You'll see this scroll throughout, and we'll go ahead and fill it out, and that can kind of act as like a take-home strategy for you all if you're looking at this multi-cloud moving data strategy that we have here for your enterprise. So let's take, yes, this session is recorded. So let's take this idea of individual clusters per application and just kind of toss it out. It's bad for your ops engineers. It's bad for your finances. It doesn't make sense. It's a massive overhead overall. And we're not going to go back to that one huge cluster idea either. The blast radius is just far too large. It doesn't make sense there either. So let's try that approach of the medium clusters and of grouping them logically. So that's kind of our solution here at Fidelity. Instead of having hundreds of clusters, one for each application, we organize our streaming platform into a handful of different use cases, and it makes it easier to manage and also limits our blast radius. We do call this concept domain grouping. Our primary method of grouping is by the business domains within Fidelity. So we'll talk a little bit more about grouping in a second and the challenges of this. But with this, I do want to call out the isolated clusters idea. Being a financial institution, we have very critical data. And so sometimes the first idea that comes into individuals' heads on the start of their cloud journey is, I need an isolated cluster away from everyone else. And this model does support it. You can put a additional cluster into this model just fine, right? And just have only one application here. What we find over time is that is that's kind of an exception to the norm. And what we find is one application onboards to a cluster. They have one producer, one consumer, and they're just sending data into it. And it works well, and they go around and they show it off, and everybody likes it. And then some other application comes along and says, hey, I know you're really important, but I also would like that data. I think it's really cool, and why would I set up my own cluster and my own design? So over time, those isolated clusters kind of become shared naturally. Data kind of naturally wants to be shared across teams, right? So even with this model here, we get questions. We achieve layers of that isolation and collaboration, but you always have a few people looking in midway through the journey, and they say, hey, hold on. Why do you have A and B over here, but C's over here? I need all of that data together, right? And this stuff is really easy to set up, right? If you go through the Confluent Quick Start Guide, you can set up an application in a day, right? And then productionalize it within a quarter. But once you have something running in production, and then you decide you want to change this architecture, it can take years, right? So this becomes really hard and really complex quickly. So many of you understand that, and many of you get that, but that's kind of the big question of the presentation. When you look at these clusters, and you have a team that comes forward and says, "Hey, I want A and I want C over here." How do you get that? Do you just start replicating the data between those two clusters? Right? Let's talk a little bit about that. Let's talk about grouping overall. So before we go further, let's use a different example. I'm going to use the NFL here because it's football season. I'm a huge football guy. And I just love the NFL. I love watching it. So there's 32 teams in the NFL. They're grouped by two conferences. Each conference has each conference has 4 divisions, and each division has 4 teams. Now, for the most part, they're grouped into geography, right? For the most part here, but I think there we go. Sorry. So for the most part, they're grouped by geography, but not always. And one example that when people dive into this and start looking up the different divisions call out is the Dallas Cowboys down here in Texas, right? And they compare that, they look and they say, why is it grouped with the Washington Commanders and the New York Giants, and that doesn't make any sense. Why are they grouped up like that, right? And we're in Texas, so somebody probably knows this, but it's history, right? The Cowboys and the Washington Commanders have a rivalry that goes back to 1960, right? And that rivalry, that business need to have that rivalry continue and be shown often on TV trumps that geography work that they did in setting these up, right? So they have this grouping model, and they say we're going to do geography, except for a couple of cases here, right? And the Colts are another one that you can see in Indiana that's kind of another story like that. So they can be a little bit confusing, right? But when you peel it back, are there reasons for it? Absolutely. And so with this, I want to bring that back to Kafka and talk about that applied to clusters. You may say in your Kafka journey that you're going to choose one model for grouping your data. And I'm going to tell you that you're not. You can say you can group these by domain or by criticality or by latency requirements, what have you. You're not going to do that, right? Your data is going to need to be grouped by individual reasons. And so sometimes they're going to group in different ways, and sometimes they're going to need to exist across multiple clusters. And that's going to drive a lot of these conversations and a lot of this complexity, right? So what we're going to say here is do your best to group these, right? But you need to have a way to move this data and have this data exist in two places, right? So again, I'm going to bring up that 7-step strategy. We're going to fill this out as we go really quick. First of the steps is that you should group your use cases, your Kafka use cases, as best you can, but you really need to be ready for those exceptions. So let's talk a little bit about moving data now between these clusters and between these apps. So if all apps just use a vanilla Kafka consumer, they can just plug into one of these clusters and read that data off. But that's not always the simple solution. We're talking about humongous enterprises here, and we're talking about sharing of data. So the apps are just never going to be that simple. You're going to have levels of isolation. You're going to have the geographical separation to meet your business needs. And this means that we have to provide that mechanism to really just have data shared and be across multiple clusters. So one solution to this is to say, let the app teams handle it, right? Let the producing applications just make their data available wherever they need it to be. They produce it, and the consumers read that data off, right? And so they can do this in a couple of ways. They could produce directly into both, or they could do something like set up Confluent Replicator, Mirror Maker, what have you, and replicate that data. But that really doesn't solve your problem. It actually creates more problems over time. See, as you let more and more applications do this, it looks less like architecture. It looks more like spaghetti. And so this is really just not going to work, right? The problem becomes multifold when you have applications that reside across cloud providers, and they need to talk across VPCs and across all of this peering and all of this work that you have to do that's just going to be really messy really quickly, right? And then there's also the cost association, ingress and egress costs, right? So taking data out of AWS, just as an example, AWS US East 1 it's 9 cents per gigabyte. So that gets really expensive compared to moving it around within regions, right? So overall, this is really chaotic, really uncontrolled, it's not organized, and it's a headache, right? So let's take a different approach here instead, and let's talk a little bit about establishing order within this model. So let's utilize a hub and spoke model here to get the most out of our groupings. So first, we're going to define here these 2 center clusters as our shared cloud clusters. We call these our default clusters, more or less. So we call them enterprise shared clusters at Fidelity. And we're going to say, by default, these are going to be the ones you can onboard to, unless you have a need to be isolated, right? And so we're also going to say, if you need to share data across different business domains, different groups, we'll go ahead and put it in those 2 center clusters there, okay? So with this, if you need to share your data, you could either onboard directly to those clusters, or we're going to let application teams replicate to those clusters. Okay? Now, we're going to provide patterns. I'm not going to get into too much detail on how we do that. You can use Mirror Maker, you can use Replicator, what have you, right? But you allow them to replicate into that if they have that need for isolation. Or they can just get on to that cluster directly and start using it there, right? Now, between those two CSPs, we, the Kafka team, the admins of this whole platform, are going to establish a link between those, right? So we're going to set up replication between those, and we're going to own it. And the reason is because, one, that network connectivity and setting that up and configuring it is complex. So if we own it and we let others use it, that solves a lot of our issues, right? We don't have to help every single application set this up. The second thing with this is we can control those egress and ingress costs, right? So we can do things on our side, like compressing the data, or throttling it, restricting it, reviewing applications before they start to use it to make sure that they're doing things like compressing on the client side, what have you, right? So there's a lot of value in us owning that. So overall, this system is much cleaner, right? Much easier to understand. We can explain how this works to anybody within a few minutes, and it's not, sage knowledge in somebody's head. So before I go further, let's go back to the strategy guide and update that, right? We recommend that hub and spoke model, being able to identify which ones are going to be your central clusters for your enterprise versus your isolated ones. And then we exert control over that replication for that CSP bridge, right? Again, egress costs, configuration, all of that stuff, very useful to have your own control over. So now I'm going to go ahead and pass it to Michael, who's going to get into a little bit of the details of that cross-CSP replication and how we make that happen.
Great. So before we actually get into the replication patterns across CSPs, let's talk a little bit about the design of these hub clusters within a CSP first. First, because these are hubs for data sharing, resiliency is going to be extremely critical. Because of this, we're going to set up twin clusters stood up in alternate regions that are going to allow application teams to fail over. Now, internally, even these individual clusters should also span across multiple availability zones. But in the worst, like most critical of outages, we would want to have this replicated twin cluster stood up in an alternate region that's going to allow producing and consuming teams to fail over. We're also going to set up bidirectional replication between these clusters. This is going to support multiple resiliency strategies and also let application teams individually choose which region they use as primary based on the locality of their data. Now, to get back to the actual cross-CSP design itself, let's take an example. Let's say application F here wants to share data with an application team out in Azure. If we set up a single replication link from region 1 in AWS, in this example, out to region 1 in Azure, we can see that that data is actually shared out to both regions via that internal replication we introduced a little bit ago. Now, this may actually replicate data out to both regions, but it does have an issue. This isn't fault tolerant. If the replication link itself were to go down, or if either region 1 cluster in AWS or Azure were to go down, data sharing across CSPs is cut off entirely. So what can we do about this? Let's take a step back and add an additional replication link between these two region 2 hub clusters as well. In this way, even if any individual cluster or either replication link were to go down, we still have the alternate up and running that's able to share data across regions. So in that sense, we do answer all of the resiliency issues we just introduced. But remember, we did say that we have internal replication set up between regions in these clusters. So depending on the tools that you're using, you may risk data duplication occurring if the same event lands in a cluster because it's replicated from 2 separate sources. So to answer this, let's take a step back again. We do want to keep both of these external replication links across CSPs in place because that is our resiliency strategy, but let's actually cut off the internal replication between regions only in Azure in this case. Because we still have it set up in AWS, we end up getting the event shared out to both regions in Azure. So great, as far as cross-CSP itself is concerned, in this way we answer both our resiliency issues as well as our potential data duplication issues. But this isn't a solution for the native applications within Azure. Application teams that exist primarily in Azure would still want to have their data replicated out to the alternate region. They still need to be able to fail over between region 1 and 2 in Azure. So because of this, we still need to keep the replication in place in these CSPs, in Azure in this case. We only want to exclude from replication those applications that are native to AWS. So if a read replica topic from AWS is having its data shared out with Azure, we want to explicitly exclude from replication all of those read replica topics. It's worth noting that this exact same setup can be done in reverse as well. Teams native to Azure can also share their data out with AWS. And because we would exclude from replication in AWS those topics native to Azure, again, we're avoiding any data duplication issues. So this is our fault-tolerant approach. Let's actually walk through some examples now and see the replication in action. Let's start with a simple approach. Going back to application F. Let's say that it starts producing into a topic in AWS region 1. We can see that that's shared out with the alternate region within AWS via that internal replication and out to both region 1 and 2 in Azure as well via our external replication links. Data is not getting duplicated in Azure because we've excluded from replication those native AWS topics. So perfect. In a happy path scenario, we actually are able to share data out with all 3 other clusters by producing into just a single one. Now, let's actually introduce some error scenarios. let's say region 1 in AWS is to go down entirely. The producing team, in this case, ideally would transition over to producing and consuming in AWS region 2. Then, because we still have a replication link in place, we are still able to share data out with region 2 in Azure as well. Let's look at one more scenario. Let's say the producing team attempts to produce directly into Azure. Now, before I actually get into what we expect the behavior to be in this case, let's talk for a second about what we want it to be instead. Well, at Fidelity, we are a multi-cloud company, and we do drive that strategy, but typically, individual application teams would still exist primarily within a single CSP. It's just the case that the data that they're producing is desired by other teams. Those teams may exist in separate clusters within a CSP or separate CSPs entirely. Because of this, we don't actually want to grant access to these producing teams to be able to produce into these read replica topics. They shouldn't be granted access to do this. Only our external replication links that we administratively set up should be able to support this replication. This is one of the reasons that we specifically choose to use cluster linking at Fidelity to be able to share data across CSPs. Because by default, cluster linking protects data ownership by explicitly denying any rights to these read replica topics outside of the cluster link itself. No individual producers, even if they were to have access to it, could write directly into these topics. There's a couple of other benefits we like as well. The serialization and compression of events from the original source clusters are preserved when we replicate these out to alternate CSPs. And we're not saying that you can only achieve this setup with cluster linking. You could use Connect-based tools like Mirror Maker 2 or Confluent Replicator to be able to achieve this setup, but you're going to have an additional couple of hurdles to go through. One, like we were talking about with access, you need to explicitly deny rights to any other users to these read replica topics. Additionally, if you're using those tools for replication across regions within a CSP, when we were talking about excluding from replication those topics from alternate CSPs, you need to properly configure any like topic blacklists or whitelists that you're going to have with those Connect-based tools. So before we move on, let's take our key takeaways from that and add back to our strategy. The first is we want to replicate from primary cluster to primary and DR to DR using cluster linking in our case. And then point 4, we want to replicate the topics native to CSPs across regions, but topics originating from a separate CSP should all be excluded from internal replication. So with this, let's move on to talking about some of the tools alongside this setup that Fidelity uses to be able to achieve this at scale.
Thanks, Michael, for that overview of how the overall replication between CSPs work. I want to talk a moment about schema registry and schema linking for serializations. So the use of schema registry simplifies data contracts between applications. It allows the data schema to actually be updated without impacting downstream applications. And so what we see in mission critical applications is that they naturally move forward and start to use schema registry very often. So we see it as kind of a must within any organization to at least provide some form of schema registry. So with this, how do we set up schema registry in a way that it would work with a cross-CSP application here? Well, there's two ways to tackle this issue. We could either replicate the schemas across from one CSP to the other using something like schema linking, or we could go a little bit more simpler of a path here with what we call a shared global schema registry. So we took the second approach here, and we put the leader, the master, in the most used region in AWS, right? So we put that there, just make it the easiest place to read and write to. And then we're going to put the followers in all of the instances here. And that would be leader eligibility false on these. Now, this is a Fidelity-specific choice, and I'm gonna acknowledge that. When they're a follower, you can't write to them. You can only write to the leader of any schema instance. So that's really important to note. But we took that approach at Fidelity because we really care what happens inside of those schemas. We want to make sure that we carefully guard and update to those schemas. Just because there's forward compatibility, backwards compatibility, whatever, what if somebody updates that compatibility or violates it in some way, right? And then it does impact those downstream applications. It gets really, really complex when you consider that in a cross-CSP model or any data sharing model, really. So instead, at Fidelity, the only person that's able to update that schema is really our admin tools. And then we have an admin control plane that I'll talk a little bit about later that controls that ability to update that and gives access to it so that there's guardrails in place for that updating. Again, Fidelity specific, it's our choice. You may prioritize those rights, in which case you may want to go a different direction. But this is the route we took. This is really useful for a number of ways. One, relatively simple. The only thing that is of concern is that cross-CSP traffic, where we just have the connection from the leader here to the followers in Azure. But overall, that traffic is very small, right? Because we're not seeing a lot of constant writes. Instead, it's just like get info, check if there's any updates. So it's not a huge deal that there's direct connection there. The other thing is the data is available to anybody, regardless of where it lives. And so with this, the data isn't sensitive, right? It's a lot of the schema information that you're storing in schema registry, if you're using it, is a map of data. And that data may be sensitive, but the metadata around it itself usually isn't, right? It may say that there's a password or there's a social security number in that data, but it doesn't show you that information. So it's okay that other people can see it if they have access to it, right? That's okay. And so we allow it accessible to anybody inside of our organization. They can link into it and they can see just the schema information. That makes it really widely available, really easy to share that data. So that's step 5 here of our information, of our strategy. It's a must-have in our opinion, schema registry. You have to have it, but you could do something like schema linking or instead of going a centralized route. It's really dependent on your organization here, but I do think you would need to determine what your schema registry path would be. There's one more concept we'll talk about for a moment, and that's the management plane concept that I talked about before. So when you're operating at the scale Fidelity does, you really have to find a way to automate onboarding and controlling any changes within the Kafka ecosystem so that it's quick and there's a huge improvement to time to market, and everything is controlled in that way. And that's really what we use. We call a management plane here. Other companies may go down the route of Confluent Control Center, or they could do something like a standard CI/CD tool like Jenkins to make these changes, or use a Terraform module from Confluent. We built our own custom. That's our choice. It again depends on the scale you're operating or what you really want to do with it. But if you want to know a little bit more about that, we do have a Medium article out there, How Enterprises Can Centrally Manage Kafka at Scale. And this was written a few years ago. It's a good read, I think still. It's been plugged a few times by Confluent as well. Please check it out. We will share this QR code at the end as well, so don't worry too much about getting it right this second. We'll share it at the end, and a few more as well. So consider this. You have this really wonderful cross-CSP platform now, and everybody's going, wow, they can do that for us very easily. And then you have a flood of applications coming to you saying, I want to set up my event stream across CSP, or I just want to use this in general in case in the future I want to send my data across CSPs. I don't know. So you have this flood of applications team come in. You need to set up those topics. If you do that manually, that's going to be a recipe for disaster, right? There's far too many configurations that are going in. So that's what our management plane, that's what our automation is there for. So any request to a topic is going to be, for a topic is going to go to our management plane's create topic API here. And it's going to choose a deployment model based on the application's needs. So the first one would just be that single region API call where we're saying, I just need it in one region and one AWS, and then, in which case we deploy it with the configurations it needs. Even then, it's cross availability zone because we're spreading those clusters across, but it's not region resilient, right? The second model is the cross-region deployment model, which is where we're going to take the topic and create it in both regions as well as its configurations. Now, at any point, if any of those configurations that we're setting up fail, we revoke all of it. We roll it all back, right? And we say, sorry, there's an issue with that. Try again or contact us, right? But all of those configuration changes, all that replication setup, all of that's done automatically. And then, of course, the last setup here is in a similar mindset. We're going to set up cross CSP if they need to send their data across the CSPs, in which case you deploy into both of your primary regions, and then you go update the link in the alternate region, or in the alternate CSP, and it sets up your mirrored topics for you. So, all of this ensures a lot of consistency across our environments, and it's entirely automated. If you actually think about the control plane, it acts as a central layer of management and governance for that entire platform, locking down any direct changes here to that cluster. And it not only helps with topic creation, but all of the atomic operations included in topic management, granting of access to your producers and your consumers, change of your schemas, everything is done through that management plane. So this way, we really protect our clusters and lock it down. There's a strict governance system across all of it, and that only our management plane can directly alter those. Everything has to go through that management plane to make any changes. Lastly, we have a process in place that includes a version control system, and that allows us to copy our configuration from dev up to the higher environments. I'm really not going to get into too much detail on that. Again, this is why I think management plan and thinking about this stuff long-term of how you manage this is really important. But this allows us to say, hey, if it works in dev, create a copy of it, maybe change around access from a dev account to a prod account, and deploy it, right? And so all of that is really documented. And I'll also bring up another QR code here for our previous speeches that kind of go into the actual management plane concept. But overall, all that goes to say you need a way to really control those configurations and enforce a governance protocol across your environment. In order for you to really reach this stage, you have to have something along those lines. The last part of our strategy is, and I'm sorry I'm going a little bit quick, I just want to be respectful of everybody's time. The last part of this is JMX metrics and monitoring and observability. So with enabling cluster linking, there's additional JMX metrics around it that you can pull off. Many of you are probably familiar with using JMX metrics and Datadog agents to build dashboards. You can build additional ones around the lag between links. You can watch in-sync replica issues with your mirrored topics. So I recommend overall just building one of those as well. And that's going to be our step 7 here, right? Monitor and alert those issues using JMX metrics. It's simple stuff, but it's extremely important for your productionalization. We're gonna pause for just like a second there. I see like a ton of people taking photos, so we'll let you all take your photos of this, but that is our strategy here. Okay, now, the last thing we're gonna do here is we're gonna do a recorded demonstration of how all of this works together. Michael?
Sure. So, yeah, this is really the last step that we have. So, yeah, we have a pre-recorded demo. I'll probably go through this pretty quickly because we're running a bit short on time. So I'll go over some of the highlights, and then we may cut it a little bit short. So here I'm just using a couple of CLI tools. We have 4 clusters set up across 2 CSPs in 4 different regions. In AWS, we're working with US East 1 and 2. And in Azure, we're working with East US 2 and Central US. So what I'm going to do initially is just describe the topics to show that they exist in AWS, and then the process to create them in Azure next. So typically, all of these steps would be abstracted away in this management plane idea that we were talking about a little bit before. I'm just showing this manually to show how simple the process really is to set up. So with cluster linking as our tool to replicate data across CSPs, we're actually going to be setting up these topics and configs using a REST API call to some pre-existing cluster links that we've already set up administratively. By just doing that, we're able to see that the topics actually exist out in Azure now. We can describe them there, and with just that single REST API call, they were created and configured identically as the topics in AWS as well. So the next couple of steps that we'll actually do in the demo is actually do a couple of producer and consumer tests, starting off initially by producing manually a couple of messages, and then moving on to a perf test by producing a larger batch of data. I'll probably cut it off a little bit quickly, but we can see at least the first couple of producing messages, and we'll see that it actually replicates out to the other 3 clusters as well. We can consume, after producing them into AWS US East 1, we can consume in US East 2 and AWS, and then in both Azure clusters as well. The next step would be to run a perf test where we want to do a large batch of messages. In our case, we would do 50,000 1 kilobyte test messages just to see if we would have any massive latency differences between replicating across regions within a CSP and then out to alternate CSPs. I'll cut that a bit short, but In short, we don't see a significant difference between replicating out between AWS US 2 and Azure East US 2. We do see latency differences replicating out to Azure Central US, but this is completely expected. Remember, we're talking about replicating across multiple hops to get to that cluster. So if we produce into AWS US East 1, that goes out to US East 2 in AWS, and only then is it crossing CSPs out into Azure Central US. So with that, I think we'll wrap the demo and then proceed to the end.
Awesome. Thank you. And so thank you all for being a really wonderful audience. I see a lot of engagement, and I do appreciate that. And I just want to say we've presented 4 times at Confluent Current and Kafka Summit at this point. So there is a good amount of recordings and other information that I want to plug really quickly here. Again, that's the Medium article over on the far right there, Avoiding the Streaming Tsunami and all about our management plan. We also gave a rundown of that information at Kafka Summit London in 2023. That's the yellow box here, so you can watch that recording if you'd like and want to do a deep dive into that. If you're looking for this recorded already, we've done this presentation. It's got a little bit of changes to it, but the Kafka Summit Bangalore 2024 is very largely the same presentation there as well, just a little bit of updating from the last time we presented. And then lastly, I'll plug Kai Werner's blog. Kai's with Confluent, and he's used this kind of as an example of a real-world application of cross-CSP and of cluster linking. And so I also just really like his blog, and I think he's a great resource, so I'm going to plug that as well. And then lastly, over there, that's our GitHub for Fidelity. We have a lot of open source contributions and projects that we're working on that we're pretty excited with. Lastly, if you like what you see here, we have the Fidelity Jobs page if you're interested in joining us. And so with that, we'll go ahead and close for questions.